Hello, oceanography students. So we are going to talk kind of about the beginning of where our Earth came from, because that's our oceans are on our Earth. So we'll talk a little bit about how Earth came about and where our oceans came from as well. Hopefully you have already watched the video that gave you a better idea of where our solar system came from, and I'm just going to briefly review that for you before I talk about how the ocean formed. All right, so the nebular hypothesis states that our solar system formed 5 billion years ago from a huge nebula. So this is a picture of a nebula taken from the Hubble Space Telescope. And a nebula is a cloud of gas and dust. Essentially, what happens is that that cloud of gas and dust contracts inward, and enough energy is produced so that hydrogen can form into helium. And when it does, a lot of energy is produced. So essentially, the center of a solar system becomes the sun. And the nebular hypothesis has been around since the 1700s, when it was presented by Immanuel Kant. So this image is showing you kind of how a solar system forms in 4 steps. The first step is that a nebula contracts. All right. So what that means is that all the gas and dust tends to go towards the center. And then the second step is that the material that's pulled towards the center starts to rotate, and what is in the very center is going to eventually be the sun of that solar system. So now we have kind of a ball of dust and gas contracted towards the center of the nebula, and then surrounding that, that's going to be the excess gas and dust. Okay, so the remaining material is swirling around the sun, and it's forming little eddies. An eddy, we can think of it, there's eddies that form in water. So when the water is moving around, sometimes you'll see like a little swirl that forms. That's an eddy. And so in the solar system, or before it's really a solar system, it's basically still a nebula with kind of an early sun in the middle. There's all this dust that's swirling around the early sun, and as it's swirling, it forms these little eddies. Now, those eddies are basically a bunch of dust and gas that's swirling around in a circle, and the same way that the early nebula contracted, those little balls also contract. And those balls contracting are what forms the planets. All right, so that's like a very short, basic explanation, and you watched the video before, so you should have like a general idea of how this works. I'm not going to test you on specifics here, okay? So accretion is the clumping of small particles into large masses. So essentially, that's what's happening. That's what's forming the early sun and all of the early planets. Accretion is the process by which that happens. Okay, so initially, the Earth was homogeneous, meaning that the material that it was made up of was completely mixed together. Okay, so think of this as like your ranch salad dressing. Okay, you shake it up and it's all mixed together. Okay, and so that's what the early Earth was like. But then Earth's temperature increased, and the reason why it increased is because of the hydrogen turning into helium and producing all of this energy in the process. That energy basically blew a solar wind throughout the solar system and got rid of the extra dust that was in the solar system. And it also made everything really hot. Before that, the Earth was being bombarded by all kinds of material hitting it as well, okay? So there's going to be a bunch of like divots and stuff. Now, as the Earth cooled, it condensed, it shrunk in size, and all of the elements that were making it up separated by density, okay? So essentially, we start out with salad dressing that's totally mixed together, and we end up with salad dressing that is layered, okay? Think of when you mix oil and vinegar together. You've got oil sitting on the top and vinegar sitting on the bottom. So that's essentially the way that our Earth is, but it's round instead. So we're going out from the center out to the surface. Okay, so let's just take a minute to talk about density. I'm not sure what your understanding of density is, but it's measured as mass per unit volume. And that, I think if you haven't been taking science classes or physics classes or math classes to a large extent, you probably have a hard time understanding what that means. So in essence, if you took a rock and you took chalk and they were both the same size, one of them feels heavier. Which one would that be? The rock, right? Okay, so if the rock feels heavier, even though it's the same size of the chalk, what is making that happen? Well, what we would say is that the rock is denser than the chalk is. And the reason why the rock is denser is because it's made out of material that is denser, that has more mass to it than the chalk is. And also, density can also be based on how closely packed together that material is. Okay, so it's usually called rho, or mass divided by volume. And just to make a note, this is not the same thing as weight. Weight is actually mass times gravity. So your mass would be the same if here on our planet and on the moon, your weight would not be the same. Okay, so every element has a density associated with it. And our Earth is made up of lots of different elements. So what happened to our Earth is that it layered based on having the densest material in the very center, and then having less dense material above that, and less dense material above that, and so on and so forth until you get to the very surface. Okay, it's basically the same thing as when you put oil and vinegar together or oil and water together. You get layering that happens unless you shake it up and mix it. All right, so what our Earth looks like is something like this, where if you take a little piece and dig so that you can see all the way down to the very center of the Earth, what we have is a crust on the outside. And this crust is made up of silicon-based materials, basically granite and basalt. Those would be examples of that. Quartz would be another example. So that is going to be the least dense material because silica is not very dense. Okay, it's low density compared to the other elements that are making up our Earth. All right, now if you think of our Earth like an apple, the crust would be like the peel of the apple, okay, a very thin surface. Then we go down a layer and we get to what's called the mantle. The mantle is denser material. It's made out of iron and magnesium silicate. So it's denser than the crust is, and that's why it sits lower than the crust. Excuse me. Okay, so if we're thinking about the apple example, the mantle would be like the flesh that you're eating of the apple, the juicy flesh. So then if we go down another level to the very center, we have what's called the core. And the core is made up of the densest elements that make up our Earth. It's made up of iron and nickel, okay? So that's why it's at the very center. Because again, our Earth stratified or layered based on density, where the less dense material rose up to the surface. Okay, now that previous image was showing you the Earth's layers that were just based on the elements that make them up. Now we can look in a little more detail at the layers of our Earth that's based on the physical properties of each of those layers. So at the surface, we've got what's called the lithosphere. And the lithosphere is actually made up of the crust, all of the crust, plus just the very top layer of the mantle. The property of this layer is cool and rigid, meaning that it's cold when you touch it. It's not hot. And also being rigid means that it will crack if you put pressure on it. Now, if we go down a layer, we get to what's called the asthenosphere. The asthenosphere is from the base of the lithosphere to about 700 kilometers depth. Now, the important part is that it's hot and plastic. So being plastic means that when you push on it, it flows, okay? Down below that, we have what's called the mesosphere. So meso means middle. So this is going to be our Earth's middle region. It's right in the middle because there are 2 layers above it and 2 layers below it. So this layer is hot and rigid, okay? So it's got a lot of heat, but it's basically stuck there. So it's not going to be flowing. Now we go down a layer and we get to what's called the outer core. The outer core is hot and liquid, so it's flowing. And when we talk about some evidence for plate tectonics, I want you to remember this because this is what is influencing the magnetism of our Earth, is basically the core and what makes up the core. Okay, so we've got the outer core, which is hot and liquid, and then at the very center of our Earth, we have the inner core, and that is hot and rigid. All right, so we're talking about this because it is very much related to the formations of our oceans. Formation of our ocean is very much tied to this layering that we were just talking about, and the layering is how we ended up with our atmosphere. Okay, so Earth's early atmosphere was initially made up of the gases that were left over from the nebula, right? So once the solar winds came through, it blew everything away. So it blew all of that extra dust away, as well as the gases that were in our atmosphere. So what replaced that was due to outgassing. So outgassing is basically the lightest stuff in our planet coming out and getting stuck, all right? So the lightest stuff is going to be the gases. So mostly like water vapor and chlorine, methane, that kind of stuff is coming out into our atmosphere, nitrogen gas, and that is what's making up our atmosphere now. So when we have outgassing, that means that we're going to end up with water in the vapor form or in the gas form, right? You're sitting somewhere right now, and although you can't see it, there is water vapor around you, okay? That's water in the gas form. It's the same thing as if, like, let's say that you are, you have boiling water in a kettle, and you put your hand over where the opening is, and your hand ends up getting wet. And that's because you've put it over, the water vapor has gotten onto your skin, which is colder, and therefore it condenses back into a liquid. Okay, so when we think of the stratification of our planet, we have to also realize that there are gases that were coming out. So we have lots of volcanic eruptions, volcanoes putting that extra gas out into our atmosphere. Now with that, there's the water vapor. So this is going to be really important because when the water vapor comes out, it is eventually going to condense and turn back into a liquid, and that liquid is going to fall on the surface. Okay, in addition to water vapor, other gases include chlorine. So that's going to be important. All right, so the water vapor now comes out into the air and it cools and condenses, forming clouds. Those clouds then eventually release rain, and that rain fills in any of the depressions that were on the surface of the Earth, right? The Earth isn't completely smooth. It's got depressions in it. It's got little places where the water can fill up, and those would be our early ocean basins. Now, additionally, the rain that was falling, the water that was falling down, was highly acidic because it was mixed with chlorine gas. And this actually happens today. That's why it's actually really dangerous to be near a volcano when it's erupting, even if it's not a violent eruption, because that is putting out chlorine gas into the air. And if you mix that with water, you get acid rain. All right, so we have really acidic water that's falling down on our planet. And as it falls down, it touches the minerals on the surface, and those minerals end up getting dissolved into the water. So now when that water flows, it's not just pure water, it's water with stuff dissolved in it. And so what is in the depressions now, the early oceans, is pure water, but it has stuff dissolved in it, and that's how we got the saltiness of our oceans. Okay, so these minerals ran into the oceans, making it salty. Okay, so just to summarize, the volcanoes erupted, putting gases into the atmosphere. Those gases included water vapor and chlorine. The water vapor condensed into clouds and the rain fell, and it was highly acidic, so it caused the minerals in the rock to dissolve and go into the water, and that's why we end up with salty oceans, because the water that was full of minerals then ran into the oceans. Excuse me. Today, our oceans cover 70% of Earth's surface. Now, the way that oceans form today is very different from the way that oceans formed in the past. Okay, so basically, what I just described is how all this water got here. When we talk about plate tectonics, we will actually learn about the kind of geography and why oceans are where they are right now, and what's going on in the movement of our continents as well. Okay, if you have any questions, please post those questions under the weekly discussion. And the next video that you're going to be watching is about geography. So just kind of like a little basic geography lesson, as well as learning about our major oceans. Okay, and I will see you guys on Thursday.